Hey, Mr. Long, this is FRQ number 1. So part A asks to draw out all the forces at play. So here's our incline, and here's the box. The FG is going to be pointing straight down, not necessarily along any axis. And the FN will be pointing diagonally from the top of the box along the y-axis and will be smaller because the FN is a component of the absolute value of FG. And then we have the FK moving in this direction because FK is going to be the frictional force opposing the movement of the box. So part B then asks for theta. So we set up the equation in the x direction, sigma force equals mass times acceleration, which can be rewritten as FGX minus FK equals MA. And then from there, mg sine theta minus mu k mg cosine theta equals ma. So then put a divider here. Then in the y direction we can do the same overarching formula, sigma force equals mass times acceleration, but in this case it would be rewritten as FGY minus FN equals MA, which can be even further expanded into mg cosine theta minus mg cosine theta equals MA, and then 0 equals MA. We set these two equal to each other, so mg sine theta minus mu k mg cosine theta equals 0. Add mu k mg cosine theta to both sides to get mg sine theta equals mu k mg cosine theta, and we can cancel out mg because it's equally present on both sides. Sine theta equals mu k cosine theta divided by cosine theta to isolate for mu k. And sine theta over cosine theta is equal to tangent theta equals mu k. So then we plug in the value of 0.3 for mu k. So we have tan theta equals 0.3, and we take the arctan of 0.3 equals theta, which gets us to equal 16.7 to be the angle of theta on the incline. So then we have part C, which asks for the coefficient of friction for the horizontal part. So for the horizontal segment, the only force acting on it is going to be the Fk, the force of friction. So Fk equals ma in this case. So first we need to find the acceleration of the inclined segment, which we can just plug into delta x equals vit plus 1/2 at squared. Since there's no vit, and delta x is 10, we don't know a, and t is 5, so 5 squared is 25. Just simplify that. Multiply the 2 to both sides. 20 equals 25a divided by 25. 20 divided by 25 gets us to the acceleration equals 0.8 meters per second squared. Then we plug that in. Then we can plug that in again to delta x equals vf squared minus vi squared over 2a to find the vf of the inclined segment and then the vi for the horizontal segment. So we know, of course, still the delta x is 10 equals vi is going to be 0. Vf squared over 2 times 0.8, which gets us to be vf equals 4 meters per second. And then plug that in to plug that into vf equals vi plus at. Now that we know the vf for the horizontal segment is, we can just set that to equal to 0. So 0 equals, then the vi for the horizontal segment is 4 plus A, we don't know the acceleration, and we can get the t to equal 5 seconds from the graph that we're given. So then we can do that to get A equals negative 0.8 meters per second squared, because negative 4 equals 5A divided by 5 divided by 5, 0.8, negative 0.8 equals A for that section. So then back to Fk equals Ma. Fk can be expanded into mu k times mg equals ma. We can cancel out the mass there. Mu k g equals a divided by g to both sides. Mu k, and we plug in for values here. Mu k equals 0.8 over 9.8. So we get the coefficient of kinetic friction for the horizontal segment to be 0.08. So then D asks for the distance. So we can just plug that in again to delta x equals VIT plus 1/2 AT squared. We know all of that. VI is 4 times the time, which is 5, plus 1/2 acceleration 0, negative 0.8, times 5 squared, which is again 25. Plug that in to the calculator, and we get delta x equals 10 meters. So part E asks for the average speed. So speed equals distance over time, and we know the distance to be 10 meters and the time to be 5 seconds. So that gets us to 2 meters per second. And then part F asks for position time graphs, position and velocity time graphs for the horizontal segment. So starting with the position time graph, the final position is going to be at 10 meters, and the time is going to be at t equals 5 seconds. And the graph is going to be modeled like this, because it has negative acceleration, but it is still moving in the positive direction. And for the velocity time graph, we'll label this as 4 meters per second, and then this again as t equals 5 seconds, and it just goes straight down because of the constant negative acceleration. Okay, so part G is asking about some changes to the initial model, which one of them being horizontal segments run to d over 3. So 10 over 3 to get our new horizontal distance of 3.33 meters. Plug that into delta x equals vf squared minus vi squared over 2a. To get 3.33 equals vf squared minus 4 squared over 2 times 0.8. Move everything over to the left side and square root it, because this is squared. 3.33 times 2 times 0.8 plus 16 equals VF, and that gets you to VF equals 4.618 meters per second. And now that's going to be our VIX for when the ball starts falling, but to find the time, we're going to have to plug this into delta Y equals VIYT plus 1/2 GT squared. There's no VIY, and the delta Y is negative 10 meters equals 1/2 GT squared. I'm going to simplify that to negative 4.9 T squared divided by negative 4.9 to both sides. So positive 2.04 equals the T squared. Square root both sides to get the time from when it leaves the top of the height to falling, 1.42 seconds. And now you multiply 1.42 times the 4.618, because the Vx is going to stay the same no matter what, to get the distance from base to equal 6.557 meters. So then H is asking if it doubles to 2H, if X will also double. So let's set up the same equation, but delta Y is negative 20. Still no, VIY equals negative 4.9 T squared divided by negative 4.9 divided by negative 4.9. Negative 20 divided by negative 4.9. That gets you to 4.08 equals T squared. Square root both sides to get the time for this one to equal 2.02. Multiply that answer of 2.02 now by the 6.557 of the VIX, and we get around 13.247, which is not double of this, so that would be false.